lectureship last year since I'm an information theory person. That's very nice, so I'm looking forward to hearing your talk.
Thank you. Can you hear me in the back? Okay, cool. Hi, everyone. First of all, thanks to Henry and Krishna for organizing this wonderful workshop and inviting me to be a part of this. Having thoroughly enjoying the workshop so far and all the excellent talks. Cool. So today I'll be talking about adaptive coding in large-scale data storage, specifically in data centers, and an interesting coding theoretic problem that emerges out of that. So this is going to be kind of a summary of multiple different works, and it's a collaboration with multiple of my students and colleagues at CMU as well as industry collaborators. So I'll mention different works as I go along the talk. So the large-scale distributed storage systems form the foundation of data systems, right? So these really large-scale systems today store exabytes of data on millions of hard disk drives. This is just in the primary tier of storage. And in this large-scale systems, failures are common. And the failures are measured. So here I'm talking about disk failures. They are measured in this metric called annualized failure rate, or AFR for short, which refers to the fraction or percentage of disks that are expected to fail in a given year. And in order to protect data against being lost due to these failures, erasure codes are commonly used. This is erasure coding at the software layer, as opposed to the previous talk where we heard coding, which is in the physical layer. Right? So this is in the distributed file systems, like the Colossus or the Google file system or the Hadoop distributed file system. So this is at the software. Okay, so now, before going into the details, so let's just make sure we are all on the same page in terms of notation. So when I say erasure codes are used in these distributed storage systems, we have this an NK code where K refers to the dimension, that is the number of message symbols, N refers to the length, or the number of code symbols. And often these codes are systematic, that is we have data symbols, which you'll see similar pictures like this, where an empty box will represent a message symbol, and this kind of colored box will represent parity symbols. So we have K message symbols, and let's use R, which is N minus K, to refer to parity symbols. So most of the results that I'll talk about today applies to general non-systematic codes as well, but almost all codes used in practice are systematic, and it's also much more intuitive to think in terms of systematic codes. So let's just keep this picture in mind. Okay, and then these codes have to meet some decodability constraints, like for example, MDS, that is maximum distance separable, which in this context corresponds to that you should be able to decode all the data using any K out of the N code symbols. Okay, so now let's take a step back and see how erasure coding gets used in distributed storage systems. I'll take this example of N equal to 9, K equal to 6 code. Since K equal to 6, we start with 6 data blocks. So in these distributed file systems, data is often divided into chunks or blocks, and then you're encoding across these chunks or blocks. So we start with 6 data blocks or message blocks. Then because N minus K is 3, you have 3 parity blocks. These are computed on, you can assume you will take 1 byte each from each of the blocks, depending on the field size. And then you create these 3 parity symbols. For example, it could be a Solomon code, and then that creates these 3 parity blocks. And these 9 data blocks are then distributed across different disks, across different servers, and often across different failure domains, like for power domains, for example, to make sure you don't have correlated failures. Okay, so this is the picture how erasure coding fits into the distributed file systems used in data centers. Okay, so now that was just showing one code word, or in the blocks corresponding to code word. So we can refer to that as a stripe. And then in this kind of zooming out picture where we have hundreds of thousands of disk drives to millions of disk drives, you'll have many, many such code words spread across. One of that is what we saw just. Okay, so now how are the parameters? So in the example that I showed was 9, 6, so how are those parameters chosen, right? So redundancy configuration in these storage systems are based on many different factors. One of them is the amount of redundancy, right? So the amount of redundancy in the system is decided by these core parameters, right? N and K. In the example that I just showed, which was N equal to 9, K equal to 6, we had 50% additional redundancy, right? Because the overhead is, if you do N or K, it's 1.5. Okay, so now how do we exactly choose N and K? So these are chosen to meet durability requirements. For example, it could be a mean time to data loss target, and based on the failure rate expected, you can choose them. In addition to that, there are other availability requirements that if a particular block is being read and that is down, you will have to reconstruct it online. That adds to the latency, and especially the tail latency. So for example, the cloud storage providers have to meet the SLOs on the tail latency. So that comes into the picture as well in choosing these parameters. So durability, availability, and performance, all these three are taken into account in choosing the parameters. And today, in most large-scale distributed storage systems, these parameters are chosen in a one scheme for all disks fashion, because that is assuming kind of an average failure rate across the disk drives in the entire cluster. So we did a study on millions of disk drives from production clusters, including at Google, NetApp, and Backblaze. And we found some interesting data. So on this plot, on the y-axis, you see AFR, that is annualized failure rate. And on the x-axis are different make models, which correspond to basically different vendors for hard disk drives and different batches. So that's what make models refer to. So what we observed is that the failure rates across these different make models vary orders of magnitude. Okay, so, and often the cluster has many of these together. So we will see how a picture looks like later. Okay, so this is one that there is orders of magnitude difference in the failure rate across different make models. And the failure rates not only varies across different make models, it also varies over time, right? So on the left here, you see this textbook bathtub, it's referred to as a bathtub curve or the hazard rate curve. On the y-axis is again AFR, and the x-axis is the age of the disk. Okay, so on the left, you have what is referred to as infancy. It's like the infant mortality rate, which is there in humans also, right? Yeah.
On the previous graph,
yeah.
Would this bathtub part of that? So did you have the different age of the disk in the graph as well?
Yes, so it's everything, and that is why there is the variation within each make model as well.
Yeah, okay.
Yes, yeah.
You can't tell us what the makes in the models are going to correspond.
We do have some information in the paper. I'll refer to two papers. These are all, so in my group, we do both computer systems research as well as coding theory. So these are works on the system side. And so we have two papers, one in FAST, which is now more on the storage systems conference, and OSDI. There are some information, but of course not all details.
Backblaze has it all.
Yeah.
Just download.
One question.
Yeah.
The definition of AFR, how do you calculate it?
It's basically an average value it's an average failure rate.
So you take
It's like annualized number, yeah. So you'll measure for a certain duration, and it's extrapolated for a year.
So the percentage of disks that are failing over 1 year?
Yes. Yeah. So coming back to this bathtub curve, so in the infancy, the failure rates are typically higher, and then they go down, and then they remain pretty stable and low for a certain time, and that's referred to as the useful life period. And then it starts creeping back up again, and that's called the wear out stage. So that's a very clean bathtub curve, which is a textbook curve. And our production failure rate study also shows a similar curve with pretty bathtub-y in nature, right? So there is infancy, useful life, not as clean as the textbook curve, of course, but there are these different phases. Okay, so now, given this, the previous picture that I showed where all disks looked alike is not the reality, right? So in reality, in the cluster, the disk drives are going to look like this, different colors refer to different levels of reliability. So it's a mix of different disks of different failure rates. A single storage cluster is going to look like this, basically. Right? So this leads to an opportunity to reduce the storage space that is used in a cluster. So basically, since the failure rates are low and pretty stable in the middle part, that is in the useful life phase, we can reduce the amount of redundancy that is used and hence achieve lower storage space requirement. Okay, so this is just a very high-level overview, and this is what we call as disk adaptive redundancy. That is, instead of considering all disks as alike and considering like an average failure rate across all the disk drives in a cluster, do disk adaptive redundancy, because all these large-scale storage clusters already have mechanisms to measure all these metrics. So one can utilize that to save storage space. So based on the evaluations, I'll not be able to go too much into the details of this, but at a very high level, the evaluation results on production cluster data from Google and Backblaze shows that if one were to do disk adaptive redundancy, you can reduce the storage space consumption up to 15% in these clusters. And due to the scale of these storage clusters, this is a significant amount of reduction in the number of disks needed, and also literally translating to monetary savings as well as operational savings in terms of energy and human capital involved, all these things. Yeah.
Are the bad disks cheaper?
Good question. Good question. So once we published these works, many of the companies are interested in working on this also because this enables you to keep the disks longer, because now even if they are bad, you can continue to work with them by adjusting the redundancy levels. Yes, and that's definitely, and even when buying, now they can be okay with it not being perfect. Yeah. Very good question. Thank you. Yeah.
So what is the typical N and K values?
Yeah. So the N and K that I showed earlier of 9, 6 is a typical number. There are other numbers, like for example, Facebook or Meta in their data warehouse cluster, when I worked with them, it was using 1410, for example. And there are also much longer codes. So the next point is to that there are, depending on the data temperature, you would want to use different values of that. Yeah. But it's not in hundreds. Yeah.
Right.
Yeah.
I suppose that there is a right identification. So if you want to update something, you have to update all the parity.
Yes. Mm-hmm. Mm-hmm.
I suppose that's not a major issue because the read traffic is dominating.
Yes.
And not the right traffic.
Yes. Yeah. Absolutely. So it's most of the data is immutable, but not all. The write traffic is small, but update complexity is important though for exactly the reasons that you mentioned. So it's not zero, and it does lead to the amplification factor and update complexity. Towards the end, when I talk about open problems and interesting feature directions, update complexity is indeed one of them. Was there another question? Okay, so if not, let's go ahead. Yeah, so looks, right? So doing disk adaptive redundancy in large-scale clusters because of the scale can lead to significant savings. Okay, so this was one of them. So this is one reason for doing adaptive coding in storage clusters. Another reason, which as I was just mentioning, is that the data temperature, that is the frequency at which a particular data piece is read, changes over time as well. And when the data is hot, you would want to use lower rate, that is higher redundancy and shorter block lengths, because if that data is down, you will have to reconstruct on the fly. Longer codes take more time, higher tail latency. So when the data is hot, you would want to use certain parameters, and when the data gets cold, you would want to go to high rate to reduce the storage overhead. Right? So data temperature varying over time is also another reason why one wants to do adaptive coding. Okay, so these are the reasons for adaptive coding. And as I was just mentioning, that I wear two hats. a coding theorist hat as well as a computer systems researcher hat. And when I'm wearing the computer systems researcher hat, I'm super excited that we're collaborating with Google in taking this disk adaptive redundancy concept to real-world storage clusters. But at the same time, when I'm wearing my coding theorist hat, this leads to an exciting coding theory problem, and that is what will be the main focus of today's talk. And that problem is this code conversion problem. Now, when one does disk adaptive redundancy or adaptive coding, we will have to change the parameters of the code on already encoded data, right? So we have massive amount of data already encoded with certain parameters. So let's represent it by NIKI. So we have an NIKI code, lots of data already encoded using that parameters. Now we have to change that code to conform to the new set of parameters. So let's call it as a final code CF, which is NF and KF. So data encoded under CI, let's say the initial configuration, has to be transformed or converted into data encoded under CF, the final configuration. So just to be clear, it's the same information, same message blocks or the data blocks that we had seen earlier, just how the data is stored has to be changed. Okay, so it's just encoded differently now. So the naive way or the default way of doing this would be re-encoding, right? So you have the data blocks, you read the message part of it, re-encode and write the new parity blocks. However, this requires a lot of reading, right? So you have to read all the data blocks and create the new parities. And often, a large number of these stripes or its encoded blocks will have to be changed because when let's say the failure rate of the underlying disks change, there will be lots of data that needs to undergo this conversion. Okay, and this can result in spikes in the resource consumption in the cluster. So remember that whatever we are doing in terms of redundancy, fault tolerance, adaptive coding, all these are background traffic in the cluster. Right? So this is not the main job of the cluster. The main job of the cluster is to serve user requests. So that's the foreground traffic. And that should not get affected by what we do in the background. Okay? So to show you from real data, so this is from production cluster data at Google based. So if we were to do disk adaptive coding on this Google cluster, this is what would happen. So on the y-axis, using naive way of just re-encoding, on the y-axis is the total I/O of the cluster as a percentage of the I/O bandwidth of the cluster. Okay, and that's the y-axis. X-axis is the date. As you can see, there are times where 100% of the cluster I/O would be consumed just for doing this conversion if we were to go the naive route of doing conversions. And this is clearly unacceptable because this is the background traffic. And often it has to be very, very low and you cannot interfere with the foreground traffic. Right? Yeah.
So is this with the changing the cluster? This is traffic when you do the conversion.
This is if we do disk adaptive coding without any fancy coding theoretic tools. If we just do re-encoding, you read all the data blocks and create new parity blocks.
Okay, so this has to do with the new drives that have been coming online and when they.
Yeah. So when the failure rates, so this graph is a lot of work. So basically studying how the cluster builds up. So the systems paper that I mentioned earlier, and it will also come up later on, has more details. It shows how the cluster builds up over time. Disks are added incrementally as the demand grows, right? That's why in a cluster you will have disks of different ages, and when the age changes, failure rates changes, and that is when there are these kind of transitions happening, conversions, and there's this cost coming out. Yes. Yeah.
Question. So is this, we see a lot of spikes, right? So is this because most of the drives on the same stripe tend to fail in the same time? So we have the collision between those recovery traffics. So what if we evenly spread out the recovery traffic because those are background traffic, right? Let's say if we can predict the directory, that's another topic I know. But what if we proactively do this background recovery and avoid a collision? So would that be better?
Yeah, no, very good question. So this y-axis does not include any recovery. It's just conversion. If we do adaptive coding and you do this conversion, so this is just pure conversion. So no recovery, no repair. But you have a very good point that, so this is just if you do re-encoding directly, right? So we do have multiple systems work building up to a level where it won't be this bad, because you can do proactively anticipating the failure rate changes, and you can start early by giving up some gains because now you are not exactly aligned with the failure rate changes and so on. So one can do that, and I'm happy to chat about that offline. But still, there is significant improvement that one can do by having a code that is cognizant of this issue, right? So instead of trying to put band-aids at the system level of adjusting these things where the code is kind of ignorant of this aspect, if the code can also be smart enough and can handle the conversion better, it's overall a win-win. Yeah, but happy to chat more on that kind of doing proactive things. That is definitely one of the things that is part of a system that we have designed, and which is what is kind of also starting to get industry traction. Yeah. Okay. So basically, from what I want you all to take out of this is that if we do naive re-encoding, the cost on the other system resources is too high. So there is room for improvement here in order to make this right. Okay, so there are existing works in codes for distributed storage that can be, as an after the fact, can be looked at as special cases of conversion. There are also these variants of this code conversion problem where in RAID systems, when a new disk is added, you have to change the parameters, but not just changing the parameters, you also have to redistribute the data in order to make it evenly distributed across the disks. So that changes the problem because we don't have to do redistribution here when you're doing it at the software layer. And also, our community has worked a lot on the repair problem that also can be brought to bear on certain types of conversions. Like, for example, if we keep k fixed, that is the dimension fixed, and you increase the length, we can pretend that adding that additional parity is like repair of an existing previously, just pretending that existing parity, and we can use all the works that we have from this community on regenerating codes, for example, to do that. But still, these are all addressing specific parameter changes. So our goal is to be able to do general conversions from any NIKI to any NFKF in an efficient way. And this is where we propose a new framework of codes called convertible codes, which basically are designed to address this code conversion problem right at the design phase. One of the main challenges or differences from the existing works on coding for distributed storage is that here we have to handle change in the dimension. That is, we are going from Ki to Kf, right? So in order to handle this, we need to start with an LCM of Ki, Kf message symbols so that you have the same view, same set of message symbols in the initial configuration and the final configuration. So I'll soon show a picture which will make it more clear. So this is one of the exciting things here, that it's fundamentally, even to represent this, the smallest instance of this problem, to capture the essence of the problem, we need to have multiple code words in the picture. All the previous problems that our community has studied on distributed storage or in storage systems is always you can focus just on one code word and that captures the problem. So the picture here, for example, for conversion is going to look like this. So let's say we are going from NIKI code to NFKF code. So we'll have capital M is the LCM of Ki and Kf. So we are going to have M over Ki code words, multiple code words in the initial configuration. And that needs to be converted to M over Kf code words in the final configuration. Okay, so you're operating on multiple code words in the initial configuration, doing conversion, which will involve reading some parts of this, and then creating these final code words. Okay, so now, since we have multiple code words in the initial configuration and the final configuration, we will have to specify how the message symbols are partitioned across these different code words. So we will need an initial partition which maps message symbols to different code words in the initial configuration. Similarly, a final partition which says which message symbols belong to which code words in the final configuration. And we will have a conversion procedure. So let's take an example just to make this clear. So let's say we are going from a 3-2 code to a 5-3 code. LCM of 2 and 3 is 6, so we start with 6 message symbols. Let's say the initial partition is this, A, B, C, D, and E, F. And maybe the final partition is A, B, C, and D, E, F. So if the initial and final partitions are like this, then basically and using systematic codes for the visualization, this is how the initial configuration will look like. So we will have 3 code words, this 3-2 code, and after conversion, it should look like this. So we will have 2 code words of a 5-3 code. Okay, so, and this is the partitions as is specified. So A, B, C, D, E, F here, and A, B, C, D, and E, F here. Okay, so overall then, convertible codes involves the following things. So an NIKI and FKF convertible code over a field size FQ has one pair of codes, CI and CF. Partitions which specify this, which message symbols belong to which code words, both initial and final partitions, and a conversion procedure which takes from CI to CF. And all this is while meeting decodability requirements. Like for example, later on, I'll be limiting to attention to both CI and CF being MDS, it's maximum distance separable. Right? Some decodability constraint has to be maintained, both in the initial code as well as in the final code. Okay, so now what do I mean by doing better than default, right? So, and why do we think it is possible? So let's take a toy example. So let's say we are going from 5-3 to 8-6, okay? So 5-3, again, using the systematic visualization, empty boxes and the colored boxes. So we have 2 initial code words, right? So LCM of 3 and 6 is 6. So we have 6 message symbols and hence 2 initial code words, 2 parities each. And the final configuration, we'll have 6 message symbols. And these are the message symbols, and at the system level, these will be message blocks. They will be intact, they will continue to be stored where they are stored, they are not moved. Now we have to create these new 2 parities blocks, okay? So why we hope to be able to do better is, I'll show in this example that we would want to design a code, ideally, here in this case, that we can generate these 2 parity symbols just by accessing the parity symbols of the original code and not having to touch the data symbols at all. So I'll just, to convince that this is possible and to create hope that we can do better than the naive encoding, this is an example for this toy parameters that it is possible. Okay, so with this code, I don't expect to work through the math here. I hope you'll all trust me that this really works. And here these things are chosen using the primitive elements of the field and so on. So later on, I'll show a generalized construction of this. But here, this part just shows the parity part of the generator matrix. So this is how we will generate the 2 parities of the initial code word. This and this is the same code. As you can see, it's the same parity matrix. And while doing conversion, you will read the 2 parities from this P1 and P1 prime, for example, and then multiply with this matrix to create the final parity matrix for the final code. Okay, so in this example, you can just read the parities and then create the final parities. So the example that I showed was of merge type of conversion. That is, we took multiple initial code words and then merged it into one final code word. Okay, so, but there are other types of conversions called split, where you take one and split into multiple, and then generalized versions of this, and then finally the general regime, which takes us from any NIKI to any NFKF. So this is just a taxonomy of different classes of conversions. This just helps us to break the problem into smaller parts. And once you have constructions for all these things, we can combine them to enable conversions from any parameters to any parameters. And this is how, as I just mentioned, merging is merging multiple code words into one final. So KF will be some lambda I times KI. Split is the opposite. You take one code word and split into multiple. So here KI will be some multiple of KF. Okay, so that's the taxonomy of different classes of conversions. And now when we want to measure the cost of conversions, there are two main costs, as we saw in the previous talk as well. One is the access cost, which is basically number of nodes or the disks that you will have to touch in order to do conversion. And two is the conversion bandwidth, which is the total amount of data transfer that you have to do. Okay, so roughly these two correspond to the actual costs in the cluster, which corresponds to the bandwidth of the IOPS thing, and also the latency of having to move the spindle, for example, in this. So the two different costs. Yes.
Quick question. So I think there's a difference between the original and naive scheme. You read and decode and write. Versus this one. So this scheme will just carry all the errors without correcting them, right? So in the data, right? But in the original scheme or the naive scheme, the errors will be decoded and everything clean.
Yeah. So although here we don't have any errors, right? So this is at the software layer, right? So this is at the file system level. So there are no errors in it. So this is just erasures of missing. Yeah. Okay. So access cost and bandwidth cost. Okay. So on the access cost side, there are works looking at, again, as I mentioned, that these different classes of types of conversions: merge regime, split regime, and the general regime, tight lower bounds, and some explicit optimal constructions. And on the conversion bandwidth side, merge regime is much well known. On the split regime, it's tight lower bounds are not there, so its optimalities are known, but there are some constructions. So in the interest of time, I'll not be able to cover all of these things, but I'll just give a flavor of both sides because they have kind of different set of results and different techniques. Just at a very high level, I'll just highlight merge on both of them. So here is a very informal statement of the results. Okay, so this is looking at the access cost and focusing on both CI and CF. There is both the initial and final codes being linear and MDS, maximum distance separable. So that's the decodability constraint. Now, keeping that, recall that R is n minus k, and in the systematic code world, it corresponds to the number of parities. So on the y-axis is the relative savings, like 0.6 is 60% reduction. And the y-axis is RF. And the plot looks like this. That is, in this initial part, where RF is less than or equal to RI, so this point is RI. Access cost is lambda I times RF. So recall that this is merge regime, that is you're merging multiple code words, you're merging lambda I code words. And access cost is lambda I RF, corresponds that you are reading from only RF blocks, and RF is exactly the number of parities, right? So this is the toy example picture. So you're reading only the parity blocks. So you can do that in this regime. Okay, so and that was optimal there. So you can read only the parities from each of the code words and create the final code word. Or at least like this is the bound, right? So this is the lower bound. So you have to do that. But if RF is greater than RI, you cannot do better than naive re-encoding. That is, you have to access at least ki, which is the number of message symbols from each of the code words. So remember, this is the access cost. Okay, that is, you have to touch at least ki blocks in this regime. So this is because intuitively, if RF is greater than RI, you have to create more parities, and the MDS property needs that new parity to be a function of all the message symbols. So you have to touch ki at least, otherwise you will not have the MDS property. Okay, but as we will see later, you can do much better in terms of bandwidth while still maintaining MDS property. Okay, so now this is the regime where you can do better than the naive re-encoding. So how do we construct codes that meet this bound just at a very high level? Recall is looking at systematics, so generator identity part of the generator matrix. We don't have to do anything. You have designed just the parity part of the matrix. And there are some structural properties that the parity matrix has to satisfy in order for the conversion cost to meet the lower bounds. So one is superregularity, which is for the MDS property, and this block reconstructible property helps in reducing the conversion access cost. So, and as we all know, superregularity is basically any submatrix is full rank, every square submatrix, and that's just the plain MDS requirement. And the block reconstructibility property, just pictorially, is the following. So we have this PI, which is the initial codes parity matrix, and PF is the final codes parity matrix. And what block constructible property says is that you need to be able to span these subblocks of the parity matrix using RF columns of the initial parity matrix. So, and if we have that property, then you can construct this PF by reading only RF columns from these initial code words. And that's how we can meet that bound of touching only RF from each of the code words. Okay, so this is just a very high level pictorial representation. And informally, one can construct access optimal convertible codes in all regimes to meet that lower bound, that the picture that I just showed. However, it's assuming large field sizes. Okay, and the example, how the construction looks like is this. This is also the toy example that I mentioned earlier. This is just the generalized version of that. So it has this kind of a Van der Monde structure. And the theta here is the primitive element of the field. So as you can see here, the PI is the initial generator matrix parity part. PF is the final codes generator matrix parity part. And this part is just the scaled version of this part. And that's how you can construct the final parity matrix using that. So on the right here, you have the two properties that we need, right? So you need block constructible. That happens because of that. And then superregularity is where the higher field size requirement comes in. You just put in that it's like a polynomial, then you'll have certain degree polynomial, and you can say, there exist these values, which as long as the field size is large enough. And there are lower field size constructions as well for certain parameter regimes. And I'll not go too much into the details, but it has this nice combinatorial structure where we can use super regular Hankel arrays. It has these are kind of very nice array structures which have this pattern where all these numbers from the left bottom to right top are identical. And by construction, there are algorithms to construct this. By construction, they are super regular, and they were designed in the 60s or earlier for MDS code construction, but it has this nice property that is needed for convertible codes of this being block constructible because of this structure. Okay, so there are more details in the transactions paper. So I'll, in the interest of time, I'll not go into the details, but using this kind of Hankel array form, one can construct access optimal convertible codes with low field size for certain parameter regimes, not all. Okay, now that was on the access cost. Yes, Aditya. Yeah.
Okay, so here, if you look at your KIRI, that code by itself could have been operated over GF7, for example.
Mhm.
But because of your large field size requirement, you have to operate over F13.
The large field size requirement that I previously mentioned is much, much higher than 13. But here, because of using the Hankel form construction, we are able to do lower. Yes, but you're absolutely right that the field size, higher field size requirement is needed than the base, just what a plain MDS code would.
Therefore, take a hit in storage at the very beginning. I mean, so I know you have some.
No, field size doesn't affect the storage overhead at all. So field size, I mean, often actually the field size used is 256. So here, anything about
Anything
the field
below?
size is, yeah. So in the sense that you take 8 bits and that represents your symbol.
Oh, I
So
see.
because of some optimizations at the hardware level, when you do computations, you're doing it at the byte level. And so it's,
So,
so
256 is okay.
yeah, 250. And above that will incur some additional overhead, yes. Yeah.
Okay.
And the high field size that I mentioned earlier is way higher than 56, so that's not practical. Yeah. Okay, so very quickly, on the conversion bandwidth side, lowering access cost also lowers bandwidth because you're reading only from some of the blocks instead of all the blocks. But the question is, can we do even better on the bandwidth side? And the answer is yes. How the problem is modeled for the bandwidth cost is different as compared to when you're studying the access cost. So here, for the audience here who are familiar with the regenerating codes literature on the repair problem, so this is a similar approach of representing the problem using the information flow graph. But there is an interesting twist in the model here. So the link bandwidths are variable. So it's variable link capacities, and you have to optimize that, like how the distribution should be across these various bandwidths in order to optimize the conversion bandwidth. So here, this is the initial configuration, this is the final configuration, and this is the amount of data that you're reading from existing nodes. I'll not go into too much details of it, but the result looks like this. So here we will have a vector size alpha, that is, we will have the vector code as opposed to a scalar code, because when you're looking at bandwidth, having a vector code enables you to read smaller amounts of data from each code symbol as opposed to just having to read the entire symbol. So this is the reason why, for example, when optimizing for repair bandwidth, regenerating codes and piggyback codes, all of them are vector codes. And when you're looking at just optimizing for access cost, which is the locality of repair problems, they are all scalar codes. Okay, so it's the same underlying reason here. And the y-axis here is again relative savings, x-axis is the same RF parameter. So previously we were in this regime. So if you recall, we had the straight line and then the savings dropped to 0. You could not do better. But for bandwidth, you can do significantly better. Even though you cannot save in terms of access cost, you can save in terms of the bandwidth cost. Okay, so I'll just leave it at that, and it's the same picture as earlier. The left part, access optimal codes are also bandwidth optimal, whereas on the right, you can do better. And the picture for different parameters looks similar structure, but the knee of the curve is at different locations. Okay, so now as I mentioned earlier, merge, split, and then you go to general regime. Basically, if we want to do the general regime, without going into the details, just at a very high level, how it works is, now let's say you have these initial code words and you have to create these final code words. You will do certain number of merges and certain number of splits. Like for example, you will do, for this specific example, you will do certain number of generalized splits. So generalized split just refers to, you will have different parameters of the splits, and then you will do certain number of generalized merges to create the final one. So this is just a logically splitting the conversions, but ultimately you will just have one conversion procedure. Okay, so in summary, I presented this new exciting coding theoretic problem called the code conversion problem, which arose from the application of adaptive coding in large-scale distributed storage systems. presented convertible codes, which is a general framework to theoretically study this code conversion problem. We saw two metrics of conversion, access cost and bandwidth cost. There are tight lower bounds for certain parameter regimes for both access cost and the bandwidth cost, and some explicit optimal constructions, again for certain parameter regimes for both the costs. So one of the things that excites me the most about this problem is that there is high potential for real-world impact. Unlike, I would say, in the physical layer, it's much easier and faster path to getting the results into real-world systems. Although the physical layer and the other one is also exciting, but this one particularly interests me because right now, as I mentioned, there's a lot of industry interest as well in doing disk adaptive coding for the benefits on the storage space side. So these large-scale distributed storage system administrators, they are interested and willing to try out new codes in order to save on the storage space, because it's a huge cost for them. There is a BITS magazine article coming up in the upcoming issue, which is on special issue on storage. So on code conversions in storage systems, there are more details in that, but it's a magazine article. But we do have IEEE transactions on information theory papers covering the results on the coding theoretic side that I mentioned. Okay, very quickly, there are many exciting open problems in this field. It's just scratching the surface so far. Lower bounds and optimal constructions for the general parameter regimes for both access cost and bandwidth cost, bounds on field sizes and lower field size and practical constructions. And also, in a storage cluster, you are not only interested in the conversion cost, but as some of the questions came up, there are other dimensions that are also of interest, like repair, keeping it efficient, keeping update complexity efficient, and so on. So it is of interest to look up all these properties at the same time and construct codes that are efficient along all these dimensions. In addition, there is also an interesting dimension to explore, which is the chain conversions, that is doing multiple conversions one after the other, because there are certain benefits if we can do adaptive coding, not just at the knee of that bathtub curves, but because it's not really a flat curve at the useful life period, there are multiple, it slowly creeps up. So if we can do multiple conversions, that is even better. And not just having one set of final parameters, NFKF, because you often don't know specific NFKF, you can have multiple target parameters to convert to. Again, there are some recent work in some of these, but there are a lot of open problems there. Thank you, and happy to take questions.
We'll take a quick question before we go to the break.
Yeah.
Would it not be easier, is there enough flexibility if you had Ki equal to Kf all the time, and you were only adjusting Ni, or Nf rather, that would be very easy, right?
Yes, that would be a much easier problem.
Why is that enough flexibility in rate adaptation?
Yeah, so the very good question. So often we also have to change K because these parameters are chosen, as I mentioned earlier, based on multiple different aspects. One is this durability aspect, right? So if we cared only about that, then we could potentially change only N, but not K. But even then, so let me mention that. So even then, so that might require having very large values of K in order to reach certain targets of storage space and meet certain MTTDL, for example. Okay, so for that reason, if we had only the dimension K fixed and only having to change N, then we will not be able to meet MTTDL for certain failure rates. Like for example, in the infancy period, when the failure rates is high, or during wear out, when the failure rates are high in both stages, we will need smaller K in order to reach that. I'm happy to chat more about this, but because if we have very long Ks, the failure rates is too high, And in order to, let's say, repair something online, in order to serve degraded reads, that is, read requests for a block which is currently down, the cost or the latency cost of that will be too high. So because of this multiple dimensions, like one is durability, another one is just availability or this tail latency for degraded reads. In order to satisfy both of these, cannot just keep k fixed and n change. So that is definitely easier if one can do that. Maybe other questions, I'm happy to chat during the break.
Yeah, maybe in the interest of time, we'll thank the speakers one more time. What we're going to do is start 15 minutes late.